Hi, everybody. Today we're going to be doing analyze a regression line for a data set. This is the very last section in Algebra 1 IXL. It's the KK, which is statistics. It's about interpreting and analyzing regression lines for data. And it's kind of the culmination of the whole course. So let's get started. Let's take a look and see what it says. Hopefully this box won't get in the way too much. Now they're going to give us a data set, and it says the counselor suspects that students signed up for too many extracurricular activities are hurting their GPA. She suspects that too many of them will cause their GPA to go down. She suspects that there, or is conjecturing, she's making a conjecture, that there is a negative relationship here. We would call this a negative correlation because she thinks that as the extracurricular activities are going up, the GPA is going to go down and it's going to suffer. This would indicate that it would have a negative slope and that a certain amount of the GPA is affected by how many extracurricular activities they have. It looks like it's possible or even probable from the data that we have here. And we're going to put this data into Desmos and analyze it. So the easiest way to copy this data is to highlight it and then use your keyboard copy function. You can't do the click and copy like this. It doesn't work. At least for me, it doesn't. So what I'm going to do is I'm going to go ahead and use my keyboard copy, which for me is Command C. For you, it might be Control C. Then I'm going to open up a new tab. And I'm going to go to Desmos. Now you can go to Desmos from here. You can do a search. It doesn't really matter. I'm going to go up to the main bar and just type Desmos. And there we have it. And we're going to go to the graphing calculator. It's a very powerful tool. And what it allows us to do is if I just click in an empty box and I type, for me, Command V, for you, it'll probably be Control V or something. I'm using a Mac, by the way. So if you use Command V for a Mac, it should work for you. Now, what this is going to do is it's going to paste this table into my into Desmos for me. Now, here's our data. These are the GPAs. These are the extracurricular activities, and these are the GPAs. And we can look at the picture over here as soon as I get out of the way. We can see that there seems to be a negative relationship here. We talk about how good a negative relationship is or how linear a relationship is by how well this data, these points, match a line. Now, if this data matches the line really, really well, it would be -1. In fact, if it were perfectly linear, I would have a -1, what we call a correlation coefficient, or R. In this case, we're not going to get a -1. We're going to get something between probably around a -0.7, if I had to guess by looking at it. Probably between -0.7 and -0.8. That's going to tell us that the data is going down over time and that there is a relationship between them and that it's fairly strong. A -0.7 is considered a strong negative correlation. Anything below that would be considered moderately negative correlated. Let's go ahead and put it in. Now to put this in, you type, of course, the Y1. Some of you already know this. Now I'm just typing the number 1 on my keyboard and it automatically put it in the subscript. I'm going to type the tilde, which is right next to the number 1 on your keyboard. You can also use the keyboard on board here, and the tilde is on the ABC section, and it's right there. If you can see my little pointer, hopefully. Anyway, I prefer to use my keyboard. I'm going to type mx1 plus b. And what this is going to do is it's going to put in what's called the least squares regression line. What this line represents is the line that is closest to all of these points. They're getting as close as they possibly can. And as I said, it's about a -0.7 or -0.8. It's right in there. It's -0.7847. This is the R value. It's called the correlation coefficient. And it looks pretty good. It looks like it follows the data. And that's what's supposed to happen. Now you could do a best fit line and adjust it yourself, and we're going to do that some other time. But for today, I'd like to interpret this just for a second, and they're going to ask you to interpret what this number means. This number tells us that these numbers up here are representing the GPA. These are the Y values. And these numbers are going down about 0.14 for every extracurricular activity that we add. So it would take quite a few. It would take about 7 extracurricular activities to kill your GPA 1 full grade level. And this B represents what would happen if what would we suspect would be someone's GPA if they had 0 extracurricular activities. Now, it makes no sense to talk about negatives over here. And so we call that a domain restriction. And in general, GPA never goes above 5. But for this example, I'm guessing that, our range is fairly narrow here. Hopefully, these people aren't going to go below 2 on their GPA, but it's possible. I would suspect that this isn't the only thing going on, and that the students that she chose, didn't specifically have that in mind, that they were looking for extracurricular activities as the only indicator. Anyway, let's go back. I know I went into way too much information. Now they're going to ask me to round this to the nearest thousandth, and I'm supposed to put the M and the B into my Y equation. This is my least squares regression line. So I'm just going to type in the numbers. Negative 0.135. One of the things you want to remember is that you do have to put the 0. Negative 0.135. Oh, I tried to put a negative in there. There we go. Accidentally had the. All right. The other part is the B value, which is the 3.465. And this represents our least squares regression line. Now they're going to ask us to interpret it. If a student signs up for one extracurricular activity, the least squares regression line predicts that the student's GPA would decrease by. Now, the way that they ask the question indicates that we don't put the negative in here. They're just asking for the absolute value of this slope, because for whatever reason, they decided that they want to talk about the change without including the negative or positive with it. So it's going to be 0.135. Remember to put the 0 in. They sometimes count that wrong if you don't. Now they want me to interpret, they want me to make a prediction. Now this is called interpolation. Extrapolation would mean going outside my data set. Interpolation goes inside my data set. Based on this diagram, it looks like it's somewhere between 3.1 and 2.4. And if I just had this data to go by and didn't have a model like here, then I would look in between these two and maybe take the midpoint. As it is, I could normally go back and look at the line and go to round to the nearest thousandth. And I could go back to my line and I'm looking for 5 extracurricular activities. And I could literally go on this line and go down to the 5. By the way, what I'm doing is I'm clicking with my mouse on the line itself with the pointer and dragging it. This will give you the points on your line. Now, you may be using your pad, but it'll work too. Now, I could go to 5, but there's a problem, and I'll tell you what it is in just a second. Hang on, let me get to 5. 5 is 2.79. Now, it just so happens that this one looks like it's rounded off correctly, and it probably, since it's rounded off to the 100th place, it's probably okay. But in the past, when I did it on the best fit line like this, it counted it wrong because this equation is rounded off and the line gives me the perfect answer. I suspect that this one won't be a problem, so I can probably use it, but you may want to have a calculator handy and type it in to the calculator. Put in the negative 0.135 times 5, and then add it to the 3.465 and round it to the nearest thousandth. I'm actually going to do that. just to double check it because I don't want to get the wrong answer. So if I put my 0.135 times 5 and, oh, dang it. I thought I could just put my negative on later. Negative 0.135 times 5. And then add that to my 3.465. I get 2.79. Yeah, it ends up being the same for my calculator. Now, like I said, in the past, it didn't work out. But the reason I suspect that this is okay is because it's not like this. So there it is, 2.79. And again, I substituted it into a calculator with this equation. And either way, I got 2.79, which is between these two, isn't it? It isn't necessarily the midpoint, but it's in between. All right, I know I gave you way too much information. I'm sure you are ready to move on and get this done. So let's take our data and copy it. Now I'm going to give you a caution. If there's any negatives inside your data, the way that IXL put the data into the chart with negatives means that you can't copy and paste it. So if there's any negatives in your data, make sure that you don't try to copy and paste it. You actually have to write it down and copy it that way. So anyway, let's go ahead and do our copy. I highlight them. Remember you can't use the click copy. You have to use the Command C for me. And I'm going to go to Desmos. Now get rid of both of these. And I'm going to a blank square. Now, if you have to put the data in by hand and you can't copy it for whatever reason, you have to hit this plus sign that's located here in the corner, and you have to put in a table. And then you can fill in the table with your data. Now, if you're going to use the copy and paste, don't put anything there. Just click into an empty square, and we hit Command V for me. And there's my data. And this is the data of the ages of children, and this is the seconds that they can get the top to spin. A 4-year-old can get the top to spin 36 seconds. A 5-year-old can get it to spin 20 seconds. And then an 8-year-old made it all the way to 71 seconds. The 10-year-old, all the 10-year-olds were 85, 63, and 74. It looks like a positive correlation. And in fact, if we look at our data, we can see that it is positively correlated. This is the correlation coefficient would be a positive somewhere around looks like 0.7 again. If I had to guess, this looks like about a 0.7, maybe a little lower. But let's take a look. It is strongly correlated to the positive. So we're going to put in our least squares regression line, and we're going to type in. Remember, it's just I'll put it on the keyboard so you can see it on the keyboard, so you can see exactly what I'm typing. So what I'm going to type is Y1. So I push Y, and then I literally just oops, I already had the Y. Sorry. So Y. Then I go to the 1, 2, 3, 1. Then I'm going to use the tilde, which is in the ABCs. It's right here. On your keyboard, it's up here in the corner. Oh, this thing's in my way. I don't think you guys can see it, but I can. Hopefully that isn't covering anything up. It's over here in this corner of your keyboard, in your number keys, and then right next to it is your tilde. Here's my tilde here. And then I'm going to type M, which is the slope, X1. Don't forget the 1. That is probably the most common error. And then don't forget the plus B. If you don't put the plus B, it's going to put the best fit that goes through 0. And it may or may not go through 0, but you need to have it anyway. There it is. So there's our best fit line. And it does have a correlation coefficient of 0.88, so it's better than I thought. If it's anywhere near 0.9, it's a really good positive correlation. So hopefully you guys can see the line here. This is our least squares regression line. The least squares indicates its distance from this line is the least we can make for all of these points, more or less. What does this slope represent? Can you think of what that means? it really doesn't make sense to round it to the thousandths, but we're going to do it. I would just simply write 8. And then I would write 8, maybe A minus 5. And there's the minus 5 really doesn't fit the data, but if you can interpret it, I'll put the interpretation if they ask for it. What it means is that a kid 0 age, we would expect to be able to spin the top -5. Well, clearly they can't spin the top at all. So we would call that a domain restriction. And the idea is that it takes about a 4-year-old before you can even be able to spin the top. Maybe a really adept 3-year-old would be able to spin it. Chances are that they wouldn't be able to get it for very long, though. In this line predicts that it would be for 20 seconds. Anyway, that's what's going on. We're going to go back to our regression line. And again, I went overboard again. And we're going to put in our values. Remember, I think it was positive 8 point something. Let's take a look and see what it was. 8.095. That's definitely rounded. The next number was a 0. And it's positive. And this is negative 5.244. And that is called your least squares regression line. There it is. Now we're going to interpret it. It says, this is in my way again. If a child were 1 year older, the least squares regression line predicts that he or she would be able to make the top spin for how many additional seconds, which is that 8.095. In the past, I kept putting in the 8 and rounding it off, but I'm going to go ahead and put in the whole thing, 8.095. It really doesn't make sense to include it to the thousands because this is a very rough estimate. But anyway, it would be 8 seconds approximately. And this one, a 9-year-old would be able to spin the top how long? So we're going to go back to our least squares regression line, and we're going to go to 9 years old. Remember, you point at it and drag. We're going to look at 9. Now, a 9-year-old would be 67.611. Now, I suspect that it's going to give us a different answer when we round these off, because remember, these aren't rounded and we're putting the data in. By the way, for those of you who are interested in chaos theory, this is sort of why chaos theory works. These little tiny differences, which are below 1,000th, make a difference in the output. Anyway, so back to our question, we have to use the rounded formula in our calculator, and we're interested in a 9-year-old. So we're going to take 8.095 times the 9-year-old, and we're going to subtract the 5.244, and it gives us 67.611. Let's see what we got on here. If I remember right, that was pretty close. 67.611. Oh, it actually worked this time again. All right. All right. Let's see what the next one is. I keep going overboard and going over explaining things. A reporter for a college magazine is writing a feature about student participation in on-campus organizations. She wants to see if there's a relationship between the student population and the number of on-campus organizations. Well, it makes sense. There would be more organizations in a bigger campus. It seems reasonable. So she recorded the number of students officially recognized student organizations for several colleges. Makes sense. This could be an actual research study. I doubt it, but you never know. It could actually be there. Again, if I copy it, I can do that. This one's going to work. Command C. I'm going to go to my Desmos, and I'm going to get rid of these. Let's move myself out of the way. And we go to a blank square, and we do our Command V. Hopefully I'm going fast enough for you. That is not it. Hang on just a minute. We got a little problem here. I hope you noticed that that is not the data that I copied. Let's go back again. I'm going to try one more time. let's do Command C and see, we're definitely getting something different. Let's see if I can close this out. So be careful. Sometimes it works, sometimes it doesn't. Yeah, this isn't working. So we are going to have to copy it by hand. So I'm going to go ahead and X this guy out. It's good sometimes to have to do that because I wanted you to see that occasionally the copy and paste doesn't always work. So we're going to copy down our data. I'll pause it so that you guys don't have to wait for me. Hang on. Let me just pause my, oops. I want to pause my, pause. Okay, I'm back. I copied this onto a separate piece of paper and then I came over and put it into a table. Remember, you do have to hit the plus and put the table in. There's my table. And I put the values in, and now I'm going to use my y1 tilde mx1 plus b. And it's going to get my least squares regression line. Now you can see we've got a little issue with where our points are. Let me get myself out of the way here so I can see it myself. Wait a minute, where did it go? Where's my points? Oh, they're way over here. Okay, hang on, let me move this out of the way. Now, there we go. Now we're getting some points. Now, the problem is our scale is way off, as you can see, because this is 10 times or 20 times as big as this one. The scale, it's hard for it to know which to do. So a good idea is to go ahead and use your graph setting. This is a toolbar. It's a little wrench up in the corner. So what I'm going to do is I'm going to change my domain and my range of my graph. And the way we do that is we just go down here for the x-axis. We're looking at our prediction is going to be somewhere. It looks like we're looking at somewhere between 2,000 students, maybe. I could go 0 up to 10,000, but I'm going to go ahead and go from 2,000 to say 10,000 students. There we go. And then for my y values are much smaller. So it looks like I want maybe from, let's go ahead and go 100 to 500. I could go 0 again, and I'll show you what the difference would be. Let's go 100 up to 500. Oop. Get rid of this. I just want to make it nice and even. There we go. And if we zoom in and out, we can adjust to see the zeros anyway. Now take a look. This looks like a really good positive correlation. It's a 0.84, so it's a reasonably good correlation. It is going up. We even hit one of our points right there. The 0.0375 indicates that it's for the population, for every time the population goes up, well, let's look at it this way. You add about 3.7. This is 3.7 over 100 if you read it. That's one way to read this. 0.0375 is 3.75 over 100. So we expect that there would be 3.75 organizations for every 100 students that we add up. In other words, another way to look at this is a 1 over about 30. That's probably the best way to look at this decimal. And if you wanted to, you could do, I think you could put m. Let me see if I can do this real quick for you. M to a fraction. And I think if you click here, let me see if I remember how to do this to a fraction. I thought it had a fraction deal on it, but I can't remember where it would be. Darn it, I was hoping I could do that for you. Nope, darn it, I can't remember. It used to be if I hovered over it, maybe if I, Nope. Darn it. Darn. I thought it gave me the number. Let me try this. 0.0375201. Oh, I saw it. There it is. Apparently it didn't do it automatically, but there's the fraction. You see it right here? So I rounded it off, 0.0375. I guess I could put the 0 in front of it. And then if I hit the fraction bar, it'll change it to a fraction for me. Supposed to. There it is. So, oh, that wasn't very helpful. This isn't reduced. So unfortunately, let's see if I can make it look a little better. There we go. All right. So this is one way to think of it. We would expect 37 over 1,000, which of course is this decimal red. If I could round this to the nearest thousand, it's actually 38 over 1,000. But let me get rid of this. I'm just going to read it. 38 thousandths, which is what we're going to have here. It has an interpretation, and we're going to go ahead and read it back over here. So we're talking about 0.038, which is rounded off. This tells us 38 over 1,000 tells us that 38 organizations would be added for every 1,000 students. Duh. I was trying to get a fraction to make it work out for you, but anyway, there it is. The B value doesn't really have much to do with anything. It's really close to 0, 0, which is what we would expect, because if a college campus had 0 students, we would expect them to have 0 organizations. In this particular case, it's negative 4.62. So in other words, we're starting out below 0. So really, really small campuses would have a fewer organizations. So anyway, it's negative 4.626. Now I went way into 626, I think. I went into way too much detail. Sorry about that, guys. 626, yep. And 0.038. Yeah, there it is. Oh, I keep doing that. Hopefully it isn't too bad. For each additional student, the least squares regression line predicts there would be, well, again, this is hard to interpret, but it's 0.038 student organizations, which really doesn't tell you anything. It's better to do the 38 over 1,000. Now this one, 7,862, that is very particular. It's in between these two, so we would expect it's going to be between maybe a little more than 361. But anyway, let's take a look at it and see. 7862. And we're going to go to 78. If we can. This is going by 10, so it's not going to allow us to do the, we could go to 7860. But we couldn't do 7862. See the problem? So we're guessing 290.283, but I'm going to go back to here and substitute it in. So we're looking at, and it's just as easy, 0.038 times 7862 minus 4.626. 294, but we're rounding it to the nearest integer. 294. Let's see if it did give it to us. Just real quick here. Nothing like 7860. Nope. We get 280 something, 290 something, it looks like, between 290 and 291. And with this one, I got, oops, if I used my calculator, I got 294. The reason is because this has been rounded off, and this number, this 0.038 is bigger than the number that's right here. And so it overestimated using my equation. So I'm supposed to use my equation. All right, now hopefully this one's going to work. Since we have decimals in there, I suspect it'll work out just fine. Oliver is a math teacher at a large school. Students have been complaining that his test problems are too wordy. Oliver is curious to know whether his wordiness is affecting student performance. Over the last several tests, Oliver computes the average number of words in each question, as well as the average percentage on the test. Interesting. I like that. It sounds like me, way too wordy. So here we go. We will copy. Let's see if I can make it easier. Command C, and we'll go to Desmos and do an analysis here for Mr. Oliver. All right, so we go into there, we're gonna do Command V, and sure enough, the decimals did work out. Now, clearly this is really off. Now, a good way to go back to the start is to go to the home, and then we can maybe scroll it in and it'll look a little nicer. Ah, there we go. Now we got a better graph, don't we? It's nice that it does so much automatically. So we didn't have to put these numbers into our wrench and everything. So this looks like a definite negative correlation. It looks like, let's see, as the average question length is going up, the student scores went down. Clearly there is an association here. There is a correlation. He definitely needs to stop talking so much, hint, hint, hint. So let's find out how much he's supposed to stop talking. Y1 tilde mx1 plus b. And here it is. It is a negative 0.88 correlation, very strong negative correlation. This is above negative 0.7, so it's a very strong negative correlation. Move myself out of the way. I think I stay in the corner for you. But anyway, here it is. Negative 0.494. Does anybody see that this is really close to negative 1/2? Negative 1/2. Think about what that means. We expect that for every extra 2 words of average for the questions, the score is going to go down 1%. That is a big deal. That negative 1/2 really means something. The 81 is if he can be really terse, if he can get his words down to the absolute minimum, they're suspecting that if he asks 0 words in each question on average, it's going to be an 81. So obviously better to be less words. So here we go. I'm going to try and follow the directions. Negative 0.494. See the 0 there? That means that we don't round up. I know you see the 9s over there and you want to round it, but no. This 0 tells us it's negative 0.494. Negative 0.494. Almost exactly negative 1/2. And the thousandth for this guy is 81.064. 81.064. For this particular situation, I would round it to negative 1/2 and 81. This is very, who knows for sure how specific that is, but it's pretty good. There we go. All right. On average, the question length increased by 1 word. The least squares regression line predicts that the average percentage score would go down by, again, decrease tells us that the negative is already included. So we expect that it will decrease by half a percent, or 0.494, 0.5%. Okay. 33.29. Again, I'm going to go ahead and put it into this equation. It's just safer. So negative 0.494, yep, times 33.29 plus 81.064, 64.61, and we're supposed to round it to the nearest thousand. So I definitely have had to do it this way. 64.61 619, 619. All right. Oh, this is interesting. This is a new one. I haven't seen this one before. A movie theater manager is studying the snack buying habits of customers. She expects that when longer movies are shown, people buy more snacks. Makes sense. Each week, she calculates the average duration of all movies being shown and the percentage of customers who buy snacks. The manager calculates the average movie duration in minutes and the percentage of customers who buy snacks. Why? Okay, so it's definitely looking like it's going up. This looks like a positive correlation. And if it is, this is called marketing analysis. And people get paid big bucks to do this kind of thing. And there's a reason, and I'll try to explain. Well, maybe not. I know you want to get this done and you're excited, but I'm almost done, so I'm going to take my time. So here it is. I'm going to copy my data, nice data, and I'm going to use my Command C. Go to my Desmos, get rid of these guys, put it in, Command V, and there's my data. Oh, wait a minute. Aha. It's not as strong a correlation because of this outlier here. The thing is, this outlier is going to kind of counteract this one. If this one would drag it down, this one kind of drags it up. And between the two, it's going to stay in between. Something that is going to happen, though, is it is going to affect our correlation coefficient. And our correlation coefficient is going to be something like, I would say this is pretty close to moderate. I would say it's right on the line of 0.7 or maybe a little lower. So let's take a look and see. Y1 tilde mx1 plus b, and right on the line, 0.703. It is considered to be a strong correlation, which is what I suspected looking at the data, but it's right on the edge. It's now there's some other things that you want to look at here. Does anybody notice right here that nothing below this line really makes any sense, because movies generally don't go below 90 minutes. The 110 seems to be increasing. Now this one was a, if I had to guess, a lot of times you want to explain why outliers occur. If I had to guess, this movie had food in it, and this movie was very gory, if I had to guess. And people generally don't want to eat snacks at the Friday the 13th movie, but they might want to eat snacks at something like Eat, Pray, Love. Okay, so anyway, just a suggestion. This one's kind of in between, so maybe it's an action movie. Anyway, it definitely looks like there's a positive correlation going on. I know you're ready to put the numbers in, so let's put them in there and show it works. 0.348, and it is a positive correlation. 0.348 does round up, round to 0.348. No, the 111 doesn't do anything. Now we have a negative 32.154. Negative 32.154. This one really doesn't have any meaning. It says that we would expect negative 32% of the people would buy snacks at a movie of 0 minutes. So if you don't show the movie, you're not going to get people buying snacks. So there it is. There's our model. Let's make sure it's the right numbers. It looks good. Didn't want to mess it up on this at this point. And we're getting there. Now we're supposed to interpret it. The average movie duration increased by 1 minute. The least squares regression line predicts that the percentage of customers who buy snacks would increase by 0.348. 0.348. Okay, I think you get where that's coming from. And if an average movie duration is 113 minutes, what percentage will this predict? So 113 minutes is up in this area. It's somewhere in this range, somewhere between these two. If we look on our calculator, we could do it, but I'm definitely going to be putting it into the equation. So you got to have a calculator handy. You don't want to do this by hand. 0.348 times 113, and we're going to subtract 32.154, 7.17%. Now, why does this matter? I'm going to get really wordy for just a second. And I really want you to see this. You see, people ask all the time, what is math good for? Why do we have to learn this? Well, you don't have to learn this. If you're going to be the guy who goes in and sweeps up the movie theater after everybody throws their popcorn on the floor and after everybody makes all the snack mess, then you really don't need any math for that. You know, you don't really have to calculate how many kernels of popcorn you swept up. However, what you really want to think about is, do you see that this right here is a big deal? This 154 and this 162 tells people that the big moneymaker for movies is selling snacks. And I guarantee there is a sweet spot here. Where after a certain amount of time, the percentage of people who buy snacks will eventually maybe go down because people are going to leave early if the movie is way too long. The English patient, you know what I mean. But when a movie hits this sweet spot, let's say that we maximize the percentage and that our research manages to maximize the percentage. And what we do is every time we send out a movie, we maximize the percentage of snack buying by increasing the previews by just the right amount to make that movie just the right length so that it increases the percentage of snack buying. How much is that worth? Well, think about it this way. Suppose you're talking about the Lowe's theaters and that you instituted the program. You're a low, mid-level executive, and you said you did this research project and you found that the sweet spot was exactly 154 minutes. Let's say that's your absolute sweet spot. And for whatever reason, there it is, the 33.51. For whatever reason, 154 minutes is exactly the right amount of time to get people to buy the most snacks they can possibly get. And it increases the snack buying by just 3% for the Lowell's theaters across the nation. Let's say that your project increased sales for that year by 3%. Your salary is probably in the $100,000 to $200,000 range. And a lot of people go, well, how in the world could he possibly be worth that while the poor guy sweeping up all the snacks and working every day is only worth $15 an hour? And this guy, supposedly his time is worth $1,000 an hour. The reason is that this guy knows something. And that 3% difference in all those 1,000 theaters might make a difference of $1 million profit one way or another. That's why he makes 100K plus and the guy sweeping up makes 10,000. Just wanted to make that clear. Why do you want to know this stuff? Well, here you go. So I hope you'll take my advice and learn some math so that you can apply it. And there we go. We did it. We went to our mastery, and I hope I'll see you back again. I'm going to be doing the geometry soon, and I'll be adding in the Algebra 2 and the pre-cal and so on. But I'll be making a little here and there. If you want a particular one in any particular subject, if you send me a message, I'll do it. So bye-bye, guys.